Okay, so as you'll recall, on Friday, we started to get into the reactions of monosaccharides. I'd like to finish that up today and also say a little bit about disaccharides and polysaccharides. It's not something I'm going to emphasize very heavily, but if you understand the reactions of monosaccharides, then that's pretty much all you need to know to understand disaccharides. One of the favorite disaccharides is, of course, table sugar. That's sucrose. But there's other ones. You'll have heard of lactose. Some of you might be lactose intolerant. Actually, I read on the internet, and it must be true, since, as you know, it's not possible to post lies on the internet. But I read on the internet that the US is the only country in the world where most people are not lactose intolerant. Don't know why that is. If that is, assuming that is true, I don't know why that is. But be that as it may, we started talking, we covered two reactions of monosaccharides on Friday. We covered exhaustive alkylation, in which we treat a monosaccharide such as this one. That one happens to be galactose, not that I really care if you know that. Most I would expect of you on looking at something like this is to know that it is not glucose, because one of the OHs is one of the the anomeric OH can of course be either axial or equatorial. But the other OHs in the CH2OH group on glucose are all equatorial, which makes glucose really easy to remember in the chair form. But be that as it may, we're going to treat this monosaccharide with an excess of an alkyl halide. Here I'm using 1-bromobutane. You also need a silver 1 salt. This could be either silver 1 oxide or silver 1 nitrate. And what happens is you exhaustively, meaning you replace all of the OH hydrogens with whatever the alkyl group is that's attached to the alkyl halide. And you will also get, in this case, silver 1 bromide precipitate. That forms an exceedingly insoluble precipitate and drives the reaction forward by Le Chatelier's principle, by removing one of the products of the reaction from the solution. Your class notes mention some things in chapter 8 and mention like the SN2 reaction. So some things in chapter 8, we didn't cover chapter 8, you're not responsible for it. And I don't think it's really a big deal that we didn't cover chapter 8. I think that probably even saved us some trouble. I think that probably only did us good. So you can, of course, ignore those things. I really should have edited the class notes, but of course, you're not responsible for chapter 8. We also talked about exhaustive alkylation, in which we're going to take our monosaccharide. This one happens to be glucose in the, let me see, alpha form. This is the alpha anomer because the anomeric OH is down. This one, of course, would be the beta anomer because the anomeric OH is up. But here it's the alpha anomer. And we're going to treat that with an excess of either an acid anhydride or an acid chloride. Here we're using benzoyl chloride. I could have picked any other acid chloride or acid anhydride. And you also need a base. Generally, it will be pyridine or triethylamine or something like that. You want to use some kind of amine base in order to soak up the acid. In this case, we would get some HCl out of this. So as a byproduct, you would get, in this case, pyridinium chloride. NH plus, Cl minus. So that's effectively an inorganic side product, where that's just a salt. We're not so concerned about that stuff. Good, so those are the reactions we covered. I want to cover about 3 more today. And then, like I said, say a little bit about polysaccharides. So, oh, should I Control Z? Oh, that's true. Oh, yeah, some of you had just walked in, but we did cover this on Friday. So this was just kind of a review. We covered exhaustive alkylation and exhaustive acylation. Also, you can watch the YouTube video and pause it on that. So Another possibility, we can also do redox of monosaccharides. I'll start with reduction. And believe it or not, this is a reaction we know already. So if we were to take, ooh, that's horrible. That's like the least straight. Actually, maybe I'll draw the 4 crossbars first. Let's take this monosaccharide in the straight chain form, since these are easiest to see in the straight chain form. And once again, if I showed you that sugar, in answer to the question, which is it? I would say I have no idea, but it is not glucose, because glucose has the OHs, sorry, right, left, right, right, and these are all to the right. So it's not glucose, it's something else. And it's a D sugar, because you see your penultimate or next to the last OH is on the right. But in order to reduce the aldehyde functional group to a primary alcohol, all we need to use is our old friend, sodium borohydride, generally an aqueous methanol solvent. You could also do the reduction with lithium aluminum hydride, by the way. I just don't know why in practice you would, since lithium aluminum hydride is much nastier and more reactive and harder to use. One tends to get fires if one is not careful. That's another thing I've all my career had difficulty persuading students of. But you see, actually, fires are bad. Fires are a bad thing, especially when you weren't planning on having it. So, and I've had a couple unintentional fires in my life, so in my lab work. So in any case, that will simply reduce the aldehyde functional group to a primary alcohol. That's a reagent we talked about in chapter, let me see now, 7. No, in chapter 9 on aldehydes and ketones. So all of these OHs, of course, will remain OHs. And compounds of this type, by the way, the reduction products of especially 5 and 6 carbon sugars, we call these things sugar alcohols. And these are used as artificial sweeteners. Many of the, you'll find them in like breath mints, chewing gum, things like that. They have the happy side benefit of also being nasty to the bacteria that are in your mouth. So they're also, at least in an indirect way, good for your teeth. I wouldn't say chewing gum replaces all other oral hygiene, but they do have that nice effect. And actually, I've noticed if you go to the baking aisle of the supermarket, they will often sell at least one kind of sugar alcohol that you can use as an artificial sweetener. It might be that you can even bake with them. I don't know. I'm not really, I'm not an expert on cooking or baking, but consult the package directions. So that's one of them. Monosaccharides can also be oxidized. Whoops. Oxidation of monosaccharides. In 2 different ways. Maybe this time I'll take glucose. Right, left, right, right. So CHO for the aldehyde group. And one oxidizing agent that you can use is aqueous bromine. The elemental halogens are all of them good oxidizing agents. Reason being that, of course, the oxidation number of the halogen in the pure element is 0. The oxidation number of any pure element is 0. And the halogen would much rather be in the -1 oxidation state. So it wants to get reduced from 0 to -1. That makes it an oxidizing agent. One of the, I taught Gen Chem as well as organic chemistry for many years. And that's one of the hardest things to teach and to learn is those annoying terms oxidizing agent and reducing agent, because oxidizing agents don't get oxidized. They oxidize something else, right? It's like a cleaning agent. Cleaning agents don't get clean, they get dirty, but they clean something else. So an oxidizing agent like bromine gets reduced, but oxidizes something else. And the product of this reaction, I actually honestly have to look each time. This will oxidize the aldehyde functional group to a carboxylic acid and nothing else, which I think is rather surprising that it's that selective. So, you know what, I'd rather write out that carboxylic acid functional group. So it leaves all of the other OH groups alone. Doesn't touch anything else. I think it's surprising that such a generic reagent like bromine is that selective. Leaves alone this CH2OH group also. And just to give you another example, it doesn't even have to be a hexose. You know, you could take, let's say, a 5-carbon sugar. I don't even know what this stuff would be. All I would know is, and all I would expect you to know, is that it's an L sugar, because my penultimate OH is on the left side. And if you treated that guy with aqueous bromine, you will get the carboxylic acid functional group. Can I write CO2H for the carboxylic acid? Save us all some time and space. You can also write COOH. That's also acceptable. You'll see that sometimes. That's up to you. That's a matter of personal preference. And these oxidation products, one of them's called an aldonic acid and one of them's called an aldaric acid, and I can never remember which is which. So if I can't remember, I don't think it's reasonable for me to expect you to remember. But you do, these two oxidation reactions, I'm about to show you another, are very clean. So aqueous bromine only oxidizes the aldehyde functional group to the corresponding carboxylic acid. Corresponding, again, meaning the compound will have the same number of carbons in it. The other oxidizing agent that is sometimes used is warm nitric acid. And I'll do glucose again, but it doesn't have to be glucose. And that also performs an oxidation. So we'll say nitric acid, and you can just write heat, or you can also use a triangle as an abbreviation for heat. But in any case, this will oxidize both the aldehyde functional group and the primary alcohol at the other end to carboxylic acids. It doesn't touch any of the other OH groups, which again, I find very surprising. Nitric acid is really nasty, and I wouldn't expect it to be so selective. I guess it just can't do anything to secondary alcohols. And likewise, you can take any old sugar you want. If you had, let's say, a 4-carbon sugar, I don't know what this one is called, and I wouldn't expect you to know that either, but I would expect you to know that it's a D sugar, because that penultimate OH is pointing to the right. And same thing, if you treated this with warm nitric acid, you can use a triangle for heat if you want to. I would expect you'd get that corresponding dicarboxylic acid. Oh, actually, I have it in your class notes. Looks like the product of aqueous bromine is the aldonic acid, and the product of warm nitric acid is the aldaric acid. I still don't expect you to memorize that. If I can't be bothered to memorize it, I don't see any point of making you memorize it. But I would expect you to know that you get these types of oxidation products. from that reaction. Good. Any questions on either of those redox reactions then? Wow, this really could be a short class. I won't rush then. Well, I'll leave that up, but let me just see if anyone's still writing. I see some of you are still writing, drawing, whatever you want to call it. There is one other monosaccharide reaction that I want to go over, and I want to take my time because I want us not to confuse that with exhaustive alkylation. It looks at first glance to be somewhat similar, but it's actually a very different kind of reaction. As it says in the class notes, that's where it talks about SN2 reactions. So the exhaustive alkylation reaction is an example of what we call an SN2 or bimolecular nucleophilic substitution reaction. All that means is that it's a substitution and the two groups change places, the H on the OH and the alkyl group on the alkyl halide. It's a substitution reaction. This one is actually not a substitution reaction, although it looks like it at first, the reaction we're going to do next. So, and this is formation of glycosides, or formation of a glycoside. And we'll define glycoside basically by the structure. But this is going to use, let's say, an alcohol, probably a fairly small one, with an acid catalyst, and it forms a full acetal. Or I can just say forms an acetal. It converts the hemiacetal at the anomeric carbon to a full acetal. So if, for example, we were to take, let's just go nuts and make up some weird sugar. Let's make this OH axial. Let's make this OH axial, and we'll leave everything else equatorial. So let's say that we treated this with ethanol, with an acid catalyst. We'll just say H+. It might also say H2SO4, for example. A catalytic amount of any acid is what you need in order to catalyze the reaction and make it go faster. But what will happen is it will convert the hemiacetal to a full acetal. Oops, I botched that up. So everything else in the molecule is untouched. It only reacts at carbon 1, the anomeric carbon. And because it does, you actually will get both anomers of the full acetal, even if you start with only one anomer in the starting material. So let me get this right. This one is going up, so that will be beta. This one is going down, so that will be alpha. And I'll get to the reason for that once I'm done drawing. But the reason for that is this is what happens is in the starting material, it opens up from the cyclic form back to the open chain form, and then recloses in order to undergo the reaction. We actually went over that also in chapter 9 on aldehydes and ketones. We talked about, oh, I'm sorry. Yes. Did I miss an H? The second one. HOH, HOH, CH. Oh, I forgot an H. You're quite right. Thank you. Oh, right. So the starting material opens back up to the straight chain form in order to undergo the reaction. And we didn't go into great detail into the mechanism of formation of hemiacetals and acetals, but I did show you all the intermediates. And I think you could get a glimpse even then as to why that is. So it basically opens to the straight chain form, does a reaction over here, and then closes back up. So when it does that, you can form either of the two anomers. The OH on carbon 5, I guess that is, can come in from either above or below that carbonyl functional group. And so you will get a mixture of anomers. So you will get both. Just to give another example, let's say we took let's say we even started with the beta anomer. Maybe this one has these two being axial. And again, I have no idea which sugar that is, and I wouldn't expect you to either. But we can tell it's not glucose because there are some axial groups. Let's say we treated this with acidic methanol. Well, I would expect you'd get a mixture of anomers of the methyl glycoside. So OCH3. So this is not a nucleophilic substitution reaction. This is more of an addition reaction. Not forgetting my hydrogen this time. And you would also get the other anom. All of the others will still be OHs. They don't react because they aren't an aldehyde or ketone functional group. But carbon 1 is an aldehyde functional group, or at least it is when it opens up to the straight chain form. Then it goes back to the aldehyde functional group, and that's what reacts. So all of these other OHs, we did say that sugars are polyhydroxyaldehydes and polyhydroxyketones. And so all of those other OHs in those many hydroxy groups are just along for the ride. They don't undergo any reaction. Good. Well, the substitute, how do you tell the difference between this and the substitution reaction? Remember, in the exhaustive alkylation, you put alkyl groups in all of the OHs because you're replacing the hydrogen. Here, you're not replacing the hydrogen. The reaction is a little more complicated than that. You're replacing the oxygen too. So it's a different kind of reaction. But the other way you tell is by the reagents. Remember, with the exhaustive alkylation, you use, I was actually going to write that down too, but I'll say it first. Remember, with that one, we used an excess of an alkyl halide and generally a silver 1 salt. Here, you just use, well, I guess I said it already. You just use an alcohol and an acid catalyst. So there's no silver 1 salt, nothing like that. So that's how you tell the difference. But it's an important question to be able to tell the difference between the two. Remember also in the exhaustive alkylation, there's no way of replacing just a few of them. It's either all or nothing. Here, it only reacts at carbon 1. Forms an acetal at C1, let's say, carbon 1. Good, other questions? Well, I'm definitely going to need the space for this if we're going to be doing disaccharides. So once you understand about forming that full acetal, forming a glycoside, as it's called, when you, and that's what the glycoside is, by the way, it's that full acetal that you get at the end. Once you understand how to do that with methanol or ethanol, let's say, then it's just a small extension, although kind of a lot to draw, but it's just a small extension to do that with any OH group on another sugar molecule. So you can take a monosaccharide and different monosaccharide, or the same, doesn't really matter. And you can pick any one of the OH groups on that second monosaccharide and do the very same thing that we just did with methanol or ethanol. And presto, you get a disaccharide that way. Disaccharides and polysaccharides. So let's say, for example, let's say that, for example, we took a glucose molecule and formed an alpha glycosidic bond between carbon 1 of the first glucose and carbon 4 of the second glucose. And I'm just writing this down so that I can remember, and then attach it to another glucose molecule. Actually, since we have the time, it's going to be a lot of drawing, but and then let's put that second glucose in the beta position. And by the way, this happens to be maltose, which is a disaccharide you might have heard of. I sure don't care if you memorize what maltose is. But what we're going to do, ooh, I can even use colors. Don't worry, you'll still get out of class early, I'm pretty sure. But since we have the time, let me show you kind of the before and after. So let's put this first glucose in the alpha anomer. That means it goes down. As an added bonus, even if you were thinking of not memorizing glucose in the chair form, we're drawing it so often you're going to wind up memorizing it anyway. And luckily, it's very easy to memorize in the chair form. Like I said, though, don't bother memorizing the Hayworth projection. There's no need. If for some reason you need it, you can get it from the chair form. I don't have it memorized either. And let's connect that to the OH on carbon 4 of another glucose. Let's even put it in a different color. Will it look bad if I use yet a third color? I kind of want to make that OH special. We'll try it. If it's bad, I won't do it again. And since this is telling us that maltose has the hemiacetal carbon in the beta anomer, we'll make that one beta, so it points up. And all we're going to do is we're going to connect up this red OH group where that OH is. We're going to do the very same thing that we just did with methanol, except it's going to drag this whole big molecule along with it. So what you get when adding those two things together should look something like this. And it's a rather distressingly large molecule, but as I hope I've begun to be able to show you this semester, even big molecules like disaccharides or, polynucleotides, nucleic acids, can be understood when you break them down to their parts. And hopefully this could even put into context some of the past material you've had in biology classes. So let me see, that's going to go up here. And this one is in the beta form. This is otherwise just glucose. So looking something like that. And it's important that this, probably both anomeric carbons are important, but it's especially important that the first glycosidic bond be alpha. In other words, the connection between carbon 1 of the first glucose and carbon 4 of the second glucose. It's important that it be alpha with respect to the first glucose molecule. If it's not, you'll still get a valid molecule, but it won't be maltose. It'll be something else. And I was going to do at least one other example of one of these too. But basically, all we've done is we've made a glycoside, except instead of OCH3, let's say, it's O-glucose. Otherwise, it's exactly the same type of molecule. So at first glance, it looks kind of big and complicated and overwhelming. And it is kind of complicated, but I would put it to you, it's not overwhelming. We can understand this structure based on what we've already covered about monosaccharides. It's just forming a glycoside with a really big and complicated alcohol. But otherwise, it's exactly the same type of reaction as we just talked about. We gave examples with methanol and ethanol. And I do want to do one more. This one is actually kind of interesting. Let's also do galactose with an alpha 1,4 glycosidic bond. And it doesn't have to be between 1 and 4. It can be between 1 and 2 or 1 and 3 or 1 and 6. It can be to a different OH group also. And then we'll attach that to a glucose. And that glucose will be the alpha anomer at the very end. And that, by the way, happens to be lactose. So if you are lactose intolerant or otherwise have a milk allergy, it's probably this glycosidic bond that you don't have the enzymes to handle. And if it's just simple lactose intolerance, well, you can take lactase enzyme and then go out and have your ice cream or whatever. Be that as it may. So the first one's going to be galactose. And that one is going to be alpha. So whoops. That's not alpha, that's beta. H. And I don't expect you to memorize, but I've drawn it enough times that I know that galactose is like glucose, except it differs at carbon 4. So instead of this OH being equatorial, it's axial. But as I've said, I don't really care. If you memorize that, I don't see any need. Because if I needed you to draw galactose for some reason, I could just tell you it's just like glucose, except it differs in configuration at carbon 4. And that's all I would need to tell you. So we'll connect that, trying to decide if I think it's ugly, but I think I'm committed to it by now. We'll connect that to, again, the OH at carbon 4 of a glucose molecule. And that guy will need to be in the alpha anomer also. Lots and lots of OHs. So if we add those two guys together and make a glycoside, then we should get that looks pretty terrible. That looks somewhat less terrible. We'll again make that oxygen red. That's a hydrogen, OH over here, CH2OH back here. And then we'll make the glucose molecule in blue. Wrong blue. This one's a little hard to see. And this OH will be down since it's alpha. OH equatorial, OH equatorial, CH2OH equatorial. So that's the structure of lactose. It's another disaccharide because it is two monosaccharides having come together to make a glycoside. And conceptually, it's exactly the same thing as the reaction we had on the previous page. Oops, I seem to have erased something by accident. Polysaccharides. There we go, that's better. So, and incidentally, once you understand disaccharides in principle, you understand polysaccharides, because we could keep doing this if we wanted to, and put on a third and a fourth and a 40th and a 400th. And that's how you get things like cellulose or glycogen, or what's the other one? Starch is another example of a polysaccharide. And breaking them down means nothing more or less than breaking these glycosidic bonds and separating them into individual monosaccharides. And some of those we have more of a problem with than others. Like, I believe cellulose basically passes through unchanged. Yes. Oh, yeah, they're just right next to each other. Same thing over here. They're not bonded. This H is bonded to that carbon. The question was about these two H's. This H is bonded to that carbon. And I could, if I wanted to, do another example. But actually, at this point, I would be letting you out only 10 minutes early, and I'm not even really embarrassed to do that. But I could, if I wanted to, do another example showing you how it could connect, let's say, to carbon 6 or carbon 3. But those also exist, disaccharides of that type. And sucrose is another disaccharide. It's a glucose connected to a fructose. But we don't really want to get into that because fructose, I'm pretty sure that one exists mainly as the furanose, which we didn't really talk about. So anyway, that's basically all I had for chapter 16 on sugars. We're going to start, I believe, chapter 10 on Wednesday. So that will be pretty much our last sort of traditional organic chemistry chapter. So we'll talk about carboxylic acids and acid chlorides and amides and esters and all those things. Other than that, have a great day. We'll see you Wednesday.